Thank you very much for invitation. Thank you very much for introduction. It's a great pleasure to be here for many reasons. First, that I am here telling you some kind of my life's history, my scientific life history, but not only scientific, because as Zbigniew told you, we're studying together, preparing exams together, living Poland together, and now coming back to work together again. I met him already when he was at NRC at Ottawa, and a great pleasure, hoping that his position here in Waterloo will open new possibilities. I see already after this first day possibilities to work with him and with other colleagues here at Waterloo. So coming to the subject of my seminar, I'm introducing here the terahertz optics or applications. Terahertz science and technology is kind of the fashion trend like quantum computing or spintronics, a kind of the wave on which the physicists surf, doing some interesting physics, but also showing some important applications that show for potential taxpayer that he can have some use. And probably terahertz science and technology is one of the closest to application from all these nice waves of physics. They are helping us to survive. So I will be talking terahertz plasma FETs from basic physics to first imaging application. And this is already in the title. You can understand my big satisfaction, because this is the only subject I was working in my life that I could bring it from equation to application. I will see at the end of seminar a film, publicity film of the first instrument built using this plasma FET. So the plan of seminar is very simple. I will tell you some background history and motivation of the work to introduce the newcomers, what is the technology of terahertz and what is the state of the art where we are. Then I will come to first real application products. So I will be talking about transistor, optics, and then I will present you a scanner. So historical introduction of terahertz has been made by mainly Japanese group. You can see here Professor Otani, who is chief now RIKEN in Sendai. I had pleasure to work with them in Sendai. They have 3-level building devoted only to terahertz techniques, and they producing this type of pictures. And this is the Tokyo Metro card. And in this Metro card inside you have some electrical circuits. So this is a plastic card, you see, and inside there are some circuits. And the circuits can be seen by using the terahertz radiation. That means radiation with the wavelengths of 1 millimeter, 0.5 millimeter, and shorter. Zbig is doing quantum cascade laser, 120, 230 microns. So this is also wavelengths with the sub-millimeter wave sometimes going. Sub-millimeter means that you can get a sub-millimeter resolution when making optics. And this sub-millimeter resolution allowed to show that on this Metro card of Tokyo, you see the metal connections here, and you can make a quality control of these cards, checking whether this metal circuits are not broken. If you make a little bit, you take a little bit shorter wavelengths, you can even see that this card taken from here was made by Sony. So control quality was evident from the beginning. And another application was for the agriculture, food industry. You see here the leaves, the vineyard leaves, and you see different pictures made at 300 gigahertz. And these pictures are done with different watering cycles. This picture shows, there is no much water in the vineyards. This vineyards needs watering. Now, first stage of watering, now we have been watering too much, because water is not transparent, so contrast is here by the water content. And this was another. But these pictures have been presented in the websites for 15 years. And there was no real world applications. Why? It was always the same problem. When scientists was asked how much time takes to make this picture, it was 1 hour. What they used to make 1 hour from one plastic card, you have to make it online. All these pictures on the internet, that I'm really happy that our Japanese colleagues had the courage to propose it as a future technology, they were taking like this. You have a source, you have just kind of chopper, then optical system that focalized the radiation at one point, and then you had the wave from this point back to the detector. And the sample was investigated at one point at the moment, and then you move the sample like this, X, Y, Z. So you can imagine that a few centimeters square were taking sometimes an hours. So what is the solution? Well, slow imaging, because X, Y, Z, so you need arrays, you need cameras, you need terahertz IA. And this terahertz IA was not present for a very, very long time, and now we are at the beginning that you can have a fast terahertz IA. People were talking about the bolometer camera. They're existing with bolometers, but they are not fast enough for quality control. So what do you have as a solution? Transistors for terahertz detector arrays. And this is a genius invention of dreamers, two dreamers, Michel Diakonov, the same from Diakonov, Perel, spin relaxation, or many other important solid-state physics guy. You have his picture here. He's smiling because he knows how it works. I still do not understand, but I understand enough to apply it for room temperature application. So he was dreaming about following thing. You see here for the first time in my presentation the transistor. So you have source, drain, and the gate. There are three pictures showing some red snake going on it. What is this red snake? This is imaginative presentation of the plasma waves. What is plasma waves? Charge density waves. And he told, when I have a magic factor, omega tau, much bigger than 1, that means high quality factor, that means electrons with high mobility, small dissipation, then between source and the drain, because of external perturbation, I can make a wave, like the wave on the water, or like the wave in the air, and this wave can be propagating, and if the mirrors are good enough, these metal parts, I can have a standing wave with big amplitude. So small perturbation can make a rise of resonant excitation. And with resonant excitation can be changed frequency by changing the carrier density, because you have a gate here. So it was idea of the resonant sources and resonant detectors. Sometimes when it is long, then it dumps down, but this is not interesting case. Why don't we still have resonant detectors, resonant emitters at room temperature? Because you need this magic factor, omega tau higher than 1. So we need high mobility of electrons, small dissipations. We have provided the proof, scientific proof, that resonant detection and emission exists, and then can be really gate tunable, but only at cryogenic temperatures. So not interesting for applications. So for the rest of today's talk, I will stay with this picture. You see, you have a source and the drain, and now external perturbation that you can imagine here, like alternative source coming connected between the gate and the source, will make something that we call overdamped plasma. But these are not waves like on the water. This is like waves on the honey. You try to push the wave, and it does not go. Damping is too big, because at room temperature, this magic factor is smaller than 1, mobility is small, and very difficult to make it, to inverse this relation. But it appeared that this situation, even if he didn't like this situation, because there was nothing resonant, nothing interesting for him, really for the basic physics, no new instabilities of solids that he provided for this type, we started to apply it for detection. So let us look a little bit closer on the transistor, source, drain, and gate. Let us imagine that incoming terahertz radiation is this alternative source here, and this is polarization voltage that makes more or less electrons in the channel. So it looks like this. You see here this perturbation density going now in real time, going up and down, because incoming electric field moving a little bit higher density, a little bit smaller density, and this perturbation propagates in the channel of the transistor. And at the same time, you see here this green curve going up. What is rising? This is the constant voltage between the source and drain that is established after a few cycles. Where does it come from? This is rectification. Why rectification? Well, everything is hidden in this formula here. you have a nonlinear element here. Why? Because you are modulating with this gate voltage. What does it make gate? Gate makes more electrons, less electrons, more electrons, less electrons. But the same, this alternative voltage polarized source, a little bit higher potential, smaller potential with respect to drain. So this alternative source will make electrons moving left to right, left to right. At the same time, polarization of the gate will make it more electron, less electron, more electron, less electron. So you have a resistor that have a resistance depending on the voltage. And you have, at the same time, modulation n cosinus omega t of carrier density and drift velocity. And this is for standard Ohm's law telling that the current is proportional to drift velocity multiplied by the carrier density. And you see these two cosinus together make you cosinus square. This averaging time is not zero, and this is the constant voltage between source and drain that is created at the border of the transistor. And you see also very important thing here, estimation of this efficient length. And you see this estimation has a special mathematical sign square root. And you have a length proportional to square root. This reminds you maybe Einstein relation between the diffusion of length and constant of diffusion and the relaxation time. It's similar. This phenomena is described by the diffusion, not propagation theory, but diffusion theory. And you see that L is proportional to the mobility and divided by frequency. Let us put the numbers to get an idea how big this rectification region is. And if you put the numbers, you have here L effective, 30 nanometers, 60, 90, 120, 150. And what you see here, the frequency, 100 gigahertz, 500 gigahertz, 1 terahertz. And you see for gallium arsenide, you have a typically 150 nanometer, the length of this region. And going down with frequency, not very fast because this is on the square root. So coming from 150 down to 30 nanometers when you go for higher frequencies. Silicon has a smaller mobility, 300. So 10 factor on the square root, so factor 3 here. And you see 60 nanometers down to 30 nanometers. And you see that these lengths are really lengths of nanotransistors. And the magic thing that was really surprising for many of the people, how possible I take a transistor, and people do not make a transistor that work at terahertz frequencies, and they make terahertz rectification. How is it possible? That frequency, the cutoff frequency of a transistor is 10 gigahertz, and its active element at 1 terahertz, because this is self-adjusting device. Its effective length is the sub-100 nanometer range, because only what's working part of the transistor is below L effective. So this is the magic of the physics of this phenomena. If I go to higher frequency, my transistor is smaller. My object is smaller. I cannot cut current on off at these frequencies, but I can detect it because I can, my transistor can sustain these oscillations in this very small region where the capacity of this region is very small. So this is the whole physics of the device, which shows you the beauty that nanotechnology, 150 nanometers here or 60 nanometers here, can allow you to make a device that has a good length, because of course you understand that if you have this length active, another part of the transistor is just the load resistor. You don't want to have it too much. So even you can use have a signal on the 1 micron transistor, you really want to have it comparable with effective. So you should go to nanotechnology to make it 2 times, 3 times larger than LF in practice. So this is the magic things about the physics of this phenomena. But the most beautiful thing that happened to us is that one of our friends who was the chief and now is vice president of the ST Microelectronics, very big company producing integrated circuits, invited us to his office to show the ST Microelectronics big new plant built close to the Grenoble. And we asked him, well, can you give us few transistors from your desk? And maybe you can try maybe silicon transistor can be a good detectors. And then, without making any special antenna, just using contacts as antenna, in 2004, so you know the history is not so old, we just put in a system that was looking for the signal at 700 gigahertz and we have detected this signal. Here, what is happening on axis? You have a spectral density, so voltage between source and drain. You have here modulation frequency. We are modulated signal on-off with 77 Hertz. So here you see the signal, and here you see the noise floor. And look, here's the logarithmic scale. There are many orders of magnitude. Signal to noise wafer detectors appear to be the best in the world. Just transistor, just simple silicon transistor appeared the best terahertz detector at room temperature with the very nice noise equivalent power. And the gate of this transistor was not so short. It was 120 nanometer. So this made an avalanche of different ideas, projects. People in Europe started to fight to make matrices. Because why? Because people know detectors of the terahertz radiation. They are usually Schottky diodes. But Schottky diodes, you cannot make thousands of them and having them the same, because surface is not reproducible. But transistors, you can make thousands of them, they will be identical with 1% precision, good enough to make a matrix, to make array. So to make finally an IA to see in terahertz, control quality, and all these applications can become true. So the people were rushing to make something like this. This is one of our realizations. So what you have here, you have a small transistor, you have source, drain, a gate, but you attach to the transistor metal pads, that is bow tie. This is connection of the transistor to the external world. This is external radiation coming here. You have to make this transistor connected to the external world, and you have to use the metal pads with the dimensions that are comparable with the wavelength. So you see here they have a radius of 60 nanometers, and the angle 60 degrees. This is typical bow tie antenna. You see the bow tie antenna for 300 gigahertz, and all other is for 600 gigahertz. So, and what happened? Well, we have the world record on sensitivity, but we measured only one, and matrix was not working. Matrix didn't work. Why? Because it appeared that it's very, very hard task. If you place this transistor on the silicon, then the silicon wafer is working as a waveguide. If you shine on this detector will see the radiation too, because the radiation will be propagated to wafer. So the mass production is difficult because you need certain thickness of the wafer to make it big, to make it cost efficient. But if this is thick, then radiation will go through the wafer. So you cannot make independent stuff. But I can tell you my personal history. I was working for 5 years, founded by ST Microelectronics. And when I brought the idea to making matrix, I have not seen this problem with the thickness and the guiding of modes. And I was hoping that ST Microelectronics, after so many years work together and with discoveries and common publications, will allow us participate in the matrix. But they found some very good engineer in Germany named Pfeiffer, and as he was engineering is the best thing to do, they told, we don't need you anymore. Everything is published, and I told them, wow, like, guys, we are in France, ST is in France, you are funding me for 7 years, we got a success, and we cannot go together. I mean, the national arguments does not play with ST Microelectronics, it's international company. We'll come to pick you up again if we need you. Goodbye, Mr. Knap. I was really disappointed. I was really angry about it because many years of work, of course, nice publications, but you want to finish with the metrics, and then with time, I could not see for the years the metrics on the silicon. I started to think, what can be a problem? And we found that this is probably a problem of the crosstalk between detectors and many other problems. And this is not a good way to open the market. And we find another. This is what we found 3 years ago, working with a small Polish company called Ortech, that you do not need the metrics of the detectors for terahertz on the wafer. It's even a stupid idea. Why? Because you need a precision on the wafer to make the camera on your mobile, because the wavelength is 0.5 microns, 0.3 microns. So you really need to make it on the wafer. But the wavelength for the terahertz is 1 millimeter or sub-millimeter. And then any machine that is making your computer boards can put transistors on the board with a precision of 10 micron. And it's easy. It's cheap. You can do it almost at home, or a very small company can order the boards when you can solder by machine the transistor and make 3 lines of the transistors. And this opened possibility for real-time applications. Because to make it with the big foundries, you need millions. And there is no market for terahertz. So no company will give you millions to develop something that there is no market. Will ask you, make us, well, I was at one of the meetings with the CEO of such company, and they were telling me, what, Mr. Knap, what is the market? Tell us what is the market, how many you sell per year, how much costs your production? And then I asked him, maybe you want my checkbook, take it. I am a scientist, I'm bringing you a nice idea. You have a marketing services, estimate market. But I understood they didn't come back to me because estimation of market is 0. There is no market for terahertz. So you have to open, and you have to open with something simple. And something simple is here. And we found it, I found finally the founding industry at the city of Warsaw in Poland. And the mayor of city of Warsaw told, I give you 300,000 zlotys, so this is less than 100,000 euro, and do a postal scanner. So we started. And for the postal scanner, you need 2 things. You need detectors, but you need also the source. So this is a point source of terahertz radiation, and then a special optics designed by Wojciech also, that takes a point and make a line. And this is diffractive optics, special optics, that has been designed. You see here one of the special lens, flat, cheap lens, less than $100, one lens. And this lens has a special density lines here, and they produces line, and one direction has 3 millimeter, and another, here is the 50, and here is 300, so 240. Why 240? Because this is the size of A4 envelope, so it was good for the scanner. So we had a source now that is linear, we have a detector. We have a detector, linear to put here, so we are ready to make a scanner. What kind of scanner we can do? Well, the scanner that should go 10 envelopes per second, this is the post office requirements, that can segregate the envelopes for envelopes with something else to control, to check by other methods. So this segregation you need, or the envelopes, they are clean, nothing inside, only paper, they have no contrast on the scanner, and then this segregation is necessary for the post offices. So postal scanner, this is joint laboratory between Poland and France and enterprise of Wojciech and Unipress Warsaw that constructed the postal scanner, fast Terahertz scanner. And you see again, this is detectors, different modules. To cover 240 millimeters, we had 6 modules like this, and then different optics that we have you can put on this detectors to increase sensitivity with also diffractive optics specialty of the Wojciech. And then electronics, but these are PCB boards. This is the boards like your computer, so this is a knowledge you do not need to integrate it to the silicon. Maybe in the future, when the market will be by millions, then you can integrate all this in silicon. But now space is not important. You can go and show first applications like this. So this is a mechanical construction of postal scanner. Here's this place for the source. You will put these magic lenses here to shine light here, and detectors you will place above. So this is how it looks like big photocopy machine at the moment, right? And you see the pictures here, what's going on. This lady is putting envelope is getting inside, and see on the screen the fusion of the vision, visible vision and terahertz vision. So you see some pictures of the screen. You have an envelope with a CD disk. When you send a DHL, you sign, inside there's only papers. And if you try a disk, then if this disk is sent from Canada to outside Europe, then at the custom in Europe, they will see there is not only papers, and they will send it back to DHL on the cost of DHL, and they are really angry about it. They want to see whether it's really only the paper to avoid the custom return of a mail. So they want to see whether it's only paper on it. And this is a metal blade of the chopper. when you see some flowers, this is an important thing. Some powder in envelope is difficult to see by any other method. Some people like to use X-rays. They are dangerous for humans because they are ionizing. They can make harm if you stay a long time. So there is a problem of operators and so on. But X-rays cannot see the powders. And if you have Amtrax, if you have the explosives, you cannot see them in envelopes. And this was also initiative of Japanese government to make this type of scanners to see the powder, because 99% of the drug distribution in Japan goes by the mail. You just order, and by the mail you get your happy bag for the evening. So they wanted to check it whether at Narita, and installed a similar scanner many years ago at the customs at Narita airport, but this scanner were working point by point. So the custom officers were thrown away this scanner after a few months tests, and until now there is no postal scanner at Narita airport in Tokyo. So you see some coins. Well, I will try to switch now the publicity video with the scanner. Excuse me, it can be a little bit. Let me try. You don't see it. Okay, so I have to go out of the presentation. I still don't see it. Okay. Maybe I go out totally out. Now you maybe see it. So this is a postal scanner, and I will switch it on. Come on, boy. Goes. So always a stress with these films connected to the video. So you see the box. This is a publicity of the product. The first was sold to Italy last month. So you see the envelope. Question mark, what is in this envelope? You see all the letters are still in Polish, so we should make it international. What we sold to Italy is in Italian. And you put the envelope inside, and you get on the picture on the screen. So the frequency of operation is 0.3 terahertz. And the envelope goes in front of the line of the detectors. As a matter of fact, there are 3 lines of detectors. And as a matter of fact, we take the 1-point source, we make 3 lines of it by this beautiful optics. You have the electronics with all readout, visible image, and terahertz vision are made in fusion. So you see dangerous objects in envelopes. Of course, this is for demonstration. Nobody puts CISO into the envelope, but this is the publicity agency that produces this for us. So we have plastic stuff that is also visible. Very thin plastic stuff or wood is visible in the contrast. So you can see different objects in the envelope. You cannot read what you have written inside, so you are on the safe side. Nobody will read your letters using my scanner. But you can see some biological species inside the envelope. And we pretend that it's easy to use. My personal opinion is it's really easy to use. It's a little bit too big, but we can make it smaller. It's no problem. Depends on the investment in the sources and make it 2 times smaller. My dream is to make a small machine that can be put on the secretary of each important office, that secretary can check whether there is no dangerous matter, for example, when you deliver it to the important persons in the ministry. Not so long time ago, we had in France a scandal. Somebody tried to put the letter to the prime minister with the explosive inside. So they detected by just touching and opening the envelope. Then this type of test can show you what's going on. So you see, it's mobile machine. It's operating. It's demonstrator. We are trying to put it in the value, showing to the post office, custom office, for the moment in Poland. But we have a first contact with a small enterprise that exists on this campus. This is Dairosh Sakedia, who is the owner of the company. How is the name? What is the name? You remember? Terahertz Systems? TTEX. So it's just next building. And he will probably, we still don't have signed agreement, try to put this Terahertz technology to Canada, and will provide all the matrices and detectors that you can live a little bit safer thanks to these discoveries. So my great satisfaction comes from the fact that I finally managed to end. Sorry, you have to go through all the slides now, but I will go fast. So you have seen the way that we went from equation to application. Now, if I have a few minutes, can I take 10 minutes to bring you a little bit more physics, a little bit something more fancy, because to tell transistor detects radiation, okay, rectifies radiation, it detects amplitude, but can it see a little bit more? And this is the work that we did with our friends from the Terahertz Center at Regensburg. And we have found the way how to use the physics to use not only amplitude, but also the linear circular polarization of radiation. And this is a beautiful story. We have a patent on it. So let us come back to this. You have seen this. Okay, coming radiation from one side, from this side, we put antenna between two of them, perturbates the current density here. Okay, and perturbates on the effective length that is defined by this, but you have seen that it's 100 nanometers, stuff like this. Yeah, but what would happen if you put two antennas from two sides? You will have a perturbation from left side and the right side, and if you have a long transistor, if you have a really long transistor, then you will get your signal that is proportional to the difference what you put from left side and right side. And that's all. But if you are clever enough, you know the physics of the phenomena, you know what is this characteristic length is, then you make your transistor not longer than this characteristic length, but slightly shorter, allowing perturbation from two sides interfering in the middle. And then Michel Diakonov, who works with us, found a magic formula. This signal that you detect will be difference what you detect from both sides, and there will be interference term depending on amplitudes of both sides, but also we'll have a theta here. Sinus theta is the phase difference between linear polarized radiation. That means if I put one antenna in X direction and another in Y direction, I will get the information of the phase shift. And if you remember from the optics courses, if you have an X electric field and Y electric field and the phase shift between them is 90 degrees, then you have a circular polarization, right? No, and that is brought us to experiments that we did in Regensburg. You see here the signal in voltage units, and you have here circular polarization, maximum of the signal, minimum for linear, then maximum for another circular polarization. That with our transistor, with two antennas, you can get a voltage that tells you something about the polarization. And this is something magic. Why? Because contrast in polarization is very important. If you fly with you will fly in the future with modern aeroplanes, take care. This is the piece of this airplane. This is a carbon materials, or when this is the visible image of piece of the plastic of carrossery of the plane. And it's made by the fibers and some kind of glue. When you have a 300 gigahertz image, when you make only amplitude image, you tell, oh, this part of the plane is perfect, no problem. It's uniform, there is no problem with the glue density. But when you try ellipsometric image, you check for polarization image, and you see, there are the bands like this. Then my fibers are not uniformly distributed, and this part can be broken somewhere here between because the fibers are bunched here and here. So this is additional contrast that you can get by engineering and taking into account physics of this material. So coming to the conclusion, I have shown you background history, motivation, first real applications, and the future will heading to amplitude and polarity sensitive imaging. I will show you at the end a slide about the polarization that I like very much. I'll try to make escape, yeah. And now I will go here and where is the polarization? Scanner Orteg. I am. So I have seen, yeah. So you see here this screenshot of the computer, and if you have this cosinus square shape of the polarization, that means that electric field is in this line. We have linearly polarized light. You have a real-time image of the polarization. What is doing the student here is just moving the polarizer, changing the direction of linear polarization. And you can immediately see that polarization now was horizontal, now is vertical. And this is done thanks to one of the transistors that is measures in the real time, whole 8, usually it takes half an hour, or an hour, measure all this point around. This is, you have optical system, you have a source, polarizer, lambda half, lambda 4, and then rotating stuff. And you see that immediately, thanks to one of the transistors, you see the whole polarization diagram. And you will see that once he places here the lambda 4, you can, from this linear polarization, obtain, if you agree with the axis between lambda 4 and lambda half, you can get circular polarization, and this polarization will be immediately, so he's putting now this lambda half here, so that will be shifting between x and y components of electric field. So now the point, yeah, he's fixing it, and intensity is small, the axes of these two elements are not well adjusted, and he will be turning it. And to find the position to get a perfect linear polarization, it's enough he turns and looks on the screen of the computer. It's a real-time measurement. Oh, this is very bad. This is not good diagram. This is still not good diagram. This is linear polarization again. So the axis of lambda 4 and I have agrees. Oh, this is probably a good position. Yeah. Now I make a circular, and I see it on the screen of my computer. So this is a beauty of the plasma waves in transistor, which gives you information about invisible light. And you can use this invisible light to better protect, better control the matter, and better protect for security, non-destructive quality control, and many other applications. I think I stop here. Thank you very much.
Thank you very much, Wojciech, for this very interesting presentation. The talk is open to questions.
You said that you make the Postal scanner with Terahertz, and then you show a slide that shows that some part you scan some particles in the envelope. Can this scanner tell us about the type of the particles?
Sorry, about?
Nature of the powder, for example, what kind of the powder, for example, if it's a drug, explosive, or if it's a drug, what kind of the drug?
In principle, yes, but not this version. This version is checking image for one single frequency. But you can simply imagine if you put many frequencies, 300, 400, 500 gigahertz, then explosive have different slope, different characteristics, and then by comparing with images at different frequencies, you can tell something about the nature. And of course, if we make this module, if we marry it with the module of Dairos-Sakedia that shows you spectra, but he will be looking for the spectra with his spectrometer, and he will be looking exactly on the point that will show him. He will be not looking for the good envelope, he will only on bad envelopes, and exactly in the point. So by putting spectroscopic unit to this stuff, you can find out what is the chemical nature of the powder that is inside, or other materials.
So it looks like you will be opening markets also to our local business, by combining those two things.
Yeah, of course. I mean, we have no partners in Canada except the friendship relation. So we need a scientific relation and then a business relation with your startups on the campus. Why not?
There we go.
Ah.
No longer be just the resource country. So, any more questions?
Yeah, very good question. You're absolutely right that the people, there are different type of sources. And this laboratory is fabricating QCLs. right? This is this Zbigniew. And when Dairosh is using the low temperature gallium arsenide and then the laser to pump, no, it's another source. This 300 gigahertz frequency that we use is produced by electronic source. It's source that takes 20 gigahertz and multiplies by many times to get 300 gigahertz by Schottky multipliers. This type of electronic sources have some advantages, disadvantages. They are narrowband, but they are robust. They are available, and they can be not too expensive. They do not need cryogenics, and they do not need the expensive lasers. So this is what we use now. But of course, we can think about the unit where we put this multicolor source, like multicolor QCL, or TDS, time-domain spectroscopy, this Dairosh Sakedia stuff, to the limit, to complete, and to get informations about the chemicals inside. So the source is electronic source.
So how much power you get from the source? How much power?
Source for the moment at 300 gigahertz, you have a good contrast if you have a 10 milliwatts of power. That is good enough, you have enough the contrast.
And how much power you pump it? How much is what the
Efficiency
efficiency of the source?
of the source, let me think about it. You have, you put about 10 watts power and you had 10 milliwatts, so 10 to minus 3. This is what power consumption is. But these are the sources, I can tell you, that are best choice to start. Why? Because they have a special tests. They are flying on the moon. They are not fragile for shaking, for humidity, and so on. And if you want to put one product on the market, it should be something good. You cannot put the laser, you cannot put the cryogenic machines. You can put it in the model number 2 or 3 to make it better. But if you start with the model that has cryogenics or laser or a lot of complicated optics, then you will probably kill the market. And this is not what we are dreaming of.
Actually, following up on, I would just follow up on that question. So I suppose there's not really any compelling need to go for higher frequency for the Postal scanners, right? Like 300 gigahertz is good enough resolution. But I was just wondering if going to a few terahertz is of any benefit, and whether those transistors actually would catch up with that kind of frequency, or you would have to move to some really sub-nanotechnology with that.
Well, we just discussed with your collaborator, his name is Diane, whether we can follow with frequency. Well, you see this card. Of course, it would be nice to have a more precision if possible. You go to 3 terahertz, you have more details, more precision. So at some moment, people will ask, we want to have a precision of 100 microns for some pictures, for some quality control. We are checking, for example, the quality of the soldering or welding of 2 plastic parts of the car, and then we have to use higher resolution. So we need surely higher frequencies. We did something that was simple, but if we can show the same thing with the QCLs at 3 terahertz, this will be a beautiful development, giving quality of the soldering of the cars, for example, and all still better information about the water content. For example, the modern cars are taking more and more plastics, but this is essential to check how the humidity enters to these plastics. And higher frequency, more precise you are in the determination of the water content. And another advantage of higher frequencies is that most of the spectral characteristics of explosive, of chemicals, are above 1 terahertz. So you really need QCLs, and the question whether the transistor can follow, the answer is yes. But we need a special fabrication. These transistors should shrink.
That's right.
They should be kind of like not like normal transistors, should be almost like quantum dots. I exaggerate. Quantum dot, you 10 nanometers by 10 nanometers, but you produce something, and you will do it one day. 100 nanometers by 100 nanometers, then we will reach the terahertz range. Why? Because what counts, physics gives you the same detectivity, no problem. But you see, L is proportional to square root of omega. So if you come from 300 gigahertz to 3 terahertz, then you have to squeeze dimension by factor 3. So you should go from 150 nanometers to 50 nanometers. So you fabricate a point like this with a gate 50 nanometers by 50. It will detect your QCL, and I will make you happy. We'll make images with QCL.
No problem.
Good, very good.
The right place.
Publicly declared. I don't remember. Please remember, now he has to do it.
Sorry.
How much would one of these scanners cost? I'm assuming more precise ones cost more,
Yeah.
or
This first demonstrator, as I told you, costed around 100,000 euros. So it's not the market price, it's the price of the engineering and a lot of hours and so on. But this device can go below 50,000 euros, and for a higher number there is no reason why the small, maybe not 300, but 140 gigahertz or 100 gigahertz scanners that do not need much resolution can go down even to 10,000 euros. This is our cost estimation. It could be really, and we compared what people do for the X-ray scanners and so on, can be comparable. So it's not excluded that we will enter with this as a complementary modules for X scanner, because the prices of the electronic sources and these detectors are not so big at the moment and will be decreasing if we make a massive production. But in this case, we need the wafers specially designed for good antennas and so on.
From this cost, how much is the source, you know?
Now, at the moment, we have a source that is more expensive at 20,000 euros. So that makes a very heavy stuff. But we bought the source. You do not need to buy the source like this, but we bought it because you are in the laboratory. So once you finish this project, you want to use it for something else. So we want to have for gas detection. This is our next step, right? So you make it perfect. So this brings the cost up. Therefore, I can reduce it by 2 by putting the very simple source inside and okay and.
All right. Well, I see no more questions. So let's thank Wojciech once again for this inspiring talk here.
Thank you, the audience, for coming here. I'm really impressed for the questions and for your presence, and I enjoyed very much.
I was not expecting anybody here. You know.
He scared me to death this morning. Oh God, Wojciech, very so beautiful weather. The seminar hall will be empty, and I see it's full. So that's a nice surprise. Thank you for being here in spite of good weather.